Hi, Eddie. Good morning.
Hi, Harry. Good morning.
How are you doing?
Good, thanks. Are you enjoying ICFP?
Yeah, it's fun. I suppose this online format allows people to do interesting things. I like it.
Oh, wait. Now it's the time for us to present our paper, Reasoning about Effect Interaction by Fusion.
All right, let's get started. So, do you remember what the paper's about?
Yes? So overall, our paper is about connecting two aspects of algebraic effects, their specifications and implementations. On the specification side, computational effects are specified by algebraic theories, describing the signatures of primitive effect for operations, and effect theories also come with a set of equational axioms characterizing the behaviors of operations. On the implementation side, effect theories are implemented by handlers, which provide models for effect operations in a way respecting the equational axioms.
This is a classical instance of separating an implementation from specification, isn't it? Where a programmer writes programs and reasons about them according to the effect theories, which are separately implemented by handlers.
Indeed, and even nicer, both effect theories and handlers are composable in their own right. Given two effect theories, you can combine them into a bigger theory containing all operations from the subtheories, and possibly adding some new equations to specify the interaction of operations from different subtheories. On the other hand, handlers are also composable by sequential composition. Given two handlers, they can be applied one by one to handle operations in a computation.
Well, that sounds really nice. So, what's the problem here? I don't really remember the details of the paper.
The problem here is that there's a missing link between the compilations of effect theories and the composition of effect handlers. It's quite interesting you don't remember what our paper is about because it is motivated by a program session started by you.
By me. So, Eddie, are you around? I'm looking at some fun stuff.
Yep, what's it?
I've been looking at effect handlers lately, and I'm trying to write a little program solving a SAT problem using effect handlers.
Sounds cool. I've heard of equational series of effects. Can you tell me more about effect handlers and your program?
Yeah, sure. Actually, I'm a bit stuck with the program, so let's take a look together. First, the code HST on the right-hand side of this slide is a standard handler for the effect of mutable state using state passing functions implementing two operations get and put that reads or writes the mutable state respectively.
Yep, and there's a theory of mutable state, which has a number of iterative equations specifying the behaviors of put and get. For example, like the one on the left side of the slide, saying that writing S into the state and immediately reading the state results in S. Does your handler respect this theory?
Yes, I've checked my handler respects all the equations of the standard theory of state.
That's nice. But then how do you use this handler?
Well, handlers can be applied to programs invoking effectful operations, such as this program, append, which reads the state and then appends one more element to the state. Then, the handler HST can be applied to it, transforming it into a state passing function. What's cool about handlers is that a lot of the language features can be implemented as handlers. For another example, the non-deterministic choice operator in logical programming can be implemented as the handler HND, which models non-deterministic computations as lists of results.
Yeah, and I also think your handler respects the usual axioms of non-determinism, such as associativity, since operations on lists respect them.
Yeah, that's right.
And can you show me a use case of this handler?
Sure. Check out this little program, choose, which picks one element from a list non-deterministically using the or and fail operations. Using this, we can write the program searching for Pythagorean triples, as well as do logic programming in it, like just as in Prolog. Applying the handler HND to this program then produces a list of all possible results. The best part of algebraic effects and handlers is that they can be easily composed. I told you earlier, I'm writing a program solving the SAT problem using state and non-determinism, and this is the program. A formula represented as a function taking a list of booleans to a boolean, and solve tries to find n booleans, making the formula true. It's basically a trivial search algorithm. The currently selected booleans are stored in the mutable state, and at each step, a boolean, true or false, is picked non-deterministically and appended to the state.
Wow, this is cool. But you said you are stuck at this program. What's the problem here? It seems to work very well.
Right, the program is fine. What puzzles me is the order of applying handlers to the program. We can either apply the handler for non-determinism first, or the handler for mutable state first. But I was surprised that only one of them gives the correct answer. And for this particular program, I can expand out the program after handling and check which one is correct. But it is already tedious and tricky for the small program, so I'm worried about trying to determine the order of composing handlers in general for larger programs.
I see. Let me have a think. I guess the way out is thinking about equations again. So when you wrote your set-solving program, you were expecting the equational axiom of state and non-determinism we talked about earlier to still hold, right?
Yeah, I did.
And did you assume some more equations characterizing the interaction of state and non-determinism for your program to work?
I think I also assumed non-deterministic operations and state operations are commutative, in the sense that two adjacent state and non-determinism operations can be swapped without changing the meaning of the program. For example, my solve program assumed reading the state before and after a non-deterministic choice is equivalent, which intuitively means that different non-deterministic branches have independent state.
I see. I think this explains why only one particular order of composing the handlers of state and non-determinism works for your solve program. Since your program assumes the commutative laws, technically you are assuming the tensor of non-determinism and state. You need to make sure your composite handler indeed respects these laws, just like you show your handlers HND and HST respect their series.
I see. Well, I totally agree with what you said, but it still seems like a tricky job to do. You know, semantically, the with handle construct is a fold on the syntax tree of programs, so the composite handler is a composite of two folds. It would be quite laborious to directly verify the composite handler respects the laws of interaction.
Indeed.
Wait, I've got an idea. Since handling is semantically a fold, some techniques from the program calculation community may be useful. They're very good at working with folds. In particular, I'm thinking about fold fusion. In this context, it means that if we can find some handler, call it HND diamond HST, such that handling with HND composed with handling with HST is equivalent to handling with this fused handler, then we can reason about the fused handler as a surrogate. The point is verifying that the fused handler respects an equation is relatively easy, and it implements that that handling with the fused handler respects the equation too, since the with handle construct is a model homomorphism of the effect theory.
Right. And then handling the fused handler is equivalent to the composite handler. It sounds a good idea, but it's not immediately clear to me how to define your diamond operator for fusing handlers.
Well, my friends Nick and Tom had a paper on optimizing effect handling by fusing handlers. I think we can tailor their technique to meet our needs. It's slightly involved to fully explain the technique, but roughly speaking, the idea is that when the first handler H1 encounters an operation that is meant to be handled by the other handler H2, then H1 doesn't need to leave the operation in the syntax tree of the computation, and instead, it can directly handle this operation using H2.
I believe it is intuitively the right thing to do, but is it really technically sound?
Well, not in general, but it can be fixed by restricting handlers to be modular handlers, which are handlers that work independently of each other. The precise definition of modular handlers is also slightly involved, but the intuition is that they exploit parametricity to guarantee that a handler doesn't mess around with operations that are meant to be handled by this handler.
I see. But there's one more serious problem. When H1 says an operation meant to be handled by H2, I don't see how you can use the clauses of H2 to handle this operation, simply because the carrier of H2 is not computed yet, right? It is only computed after H1 finishes.
Well, that's true, but I think this can be fixed by the classic CPS transformation trick. Since the carrier of the second handler will be computed eventually after H1 finishes, you can make the first handler H1 work on a continuation monad where the carrier of H2 is the final result type. Then, whenever H1 encounters an operation meant to be handled by H2, the operation can be handled by acting on the result type of the continuation monad. This sounds a bit of a mouthful, but it's essentially the same technique as Andrei Filinsky's CPS-based implementation of monadic reflection.
Cool, but it's a lot of information. I think we can write a paper about it.
Oh, good idea. So thanks, Eddie, for reminding me that, why we're speaking at ICFP. Is that really how we came up with this paper? Well, never mind. As we explained, in this paper, we reasoned about composite handlers by fusing two handlers into a single, more powerful one, just like two fighters can be fused into a more powerful one in the anime Dragon Ball Z. In the paper, we show for any two handlers H1 and H2, provided they are modular, which roughly means that they don't mess around with the operations that aren't meant to be handled by them, we can handle them into a single handler. We can fuse them into a single handler, such that handling with the fused handler is equivalent to the sequential composition of handling with H1 and H2.
With this fusion theorem, we can show a number of results relating the combinations of effect series and the sequential composition of handlers. The first one here says that all equations respected by handlers H1 and H2 respectively are still respected by their composite handler. In other words, if H1 respects a series T1 and H2 respects a series T2, then the sequential composition of H1 and H2 respects the sum of T1 and T2, which is simply the combination of T1 and T2 without any new interaction equations. But here you have to be careful. This only holds for modular handlers, and it's possible to construct counterexamples if H1 and H2 are not required to be modular. Moreover, if effect series are combined with some interaction equations, we show some sufficient conditions for the sequential composite of two handlers to respect the interaction equations. So for the motivating example we talked about earlier, both the handlers for state and non-determinism are modular handlers. Thus, we immediately know the composite handler respects all the equations from the theory of state and non-determinism because HST and HND respects them. And a result in this paper tells us for the composite handler to respect the commutativity equations of stateful and non-deterministic operations, it is sufficient to show this equality holds for each operation of state and non-determinism. Although this condition looks maybe a bit scary, it is actually simpler to work with than directly proving from the definitions, because this condition involves only the clauses of relevant operations of the two handlers, rather than recursive folds on syntax trees. For example, the clause for put is this simple function, and the clause for or is this simple function. And to show put and or are commutative under the composite handler, it is sufficient to show this equality. The equality is actually very easy to show. Expanding the definition of the cput, we get this. And with some simplification, we get this. And again, using the definition of cput, we have the needed equality. And the point here is that proving a composite handler satisfies an interaction equation in this way is much easier than a direct proof from the definitions. And there are also some more case studies in the paper, which you may find interesting. For example, we show that with the standard handler of state of stateful operations, get and put, are always commutative with any operations handled after the state handler. This is a generalization of the running example we've just seen. So these are basically what we have in the paper. And if you are interested in the interaction of effect series and their connection to handlers, or if you are interested in fusing handlers together for efficiency, which is a topic we didn't expand in the paper, but our fusion operator is certainly useful for, welcome to check out our paper. Thanks for listening.
Yeah, thanks.